Last time we started section 9.2, Multistage Experiments. We talked about the fact that all of our problems are going to show some version of a traditional tree diagram or an equivalent kind of argument. And we had taken a look at an example number 2, where we had slips of paper in a box and we were pulling out 2 slips of paper. On part A, we added the strips values together, and on part B, we're asked, does it matter if instead we had multiplied? If we were multiplying instead of adding, does it change things? So what we're going to do is we're going to go back. We've written out all the possibilities. We've just written them out with the with the addition of the 2 values instead of the multiplication. So one of the things that we have to notice, though, is that winning versus losing is really just about the numbers being even or odd, right? So don't really care whether the number is a 14 or a 10. If it's a 14 or a 10, it's both even. Are you with me? So if you really want to, you're welcome to go back and do all the multiplications of each one of those. But I'm hoping that if you just look at the values that are there, you know whether the value is even or not. How do you know if the product of 2 numbers is even? Emily, you look like you're wanting to tell me something.
If both of the numbers are even?
That would work.
Or if they're both, or if they're both odd.
Okay, so it's about whether the values themselves are even or odd. Can somebody add to that? So I agree with Emily. If both the numbers are even, you definitely have a product that's even. Is that the only way you'd have a product that's even? Yeah, if either one of them is even, it's actually going to end up being even. Yeah. So we should be able to go through, and I'll just use a red highlighter, and let's just highlight the ones that end up being even when we multiply instead of add. So for example, the first one, 4 times 6 would be even because 4 and 6 are both even. But 4 and 7 is also even because at least one of the numbers, namely 4, is even. Okay, so go through your list, highlight, mark something, all of the ones that end up being even. And then I'll give you a minute or so to do that, and then I'm going to go through and highlight them myself, and we'll make sure we're on the same page. You end up with a lot of evens? Yeah, me too. All these that have a 4 in them are even. All of them that have a 6 are even. And then the other 2 that have an 8 are even. So it's almost all of them, right? How many different options do we actually have here? Are there 10 of them? 10 total combinations or whatever ways that can work out. There are 10. And so it says, does the probability change if the 2 numbers are multiplied? And the answer, of course, is yes. And what does it change to? You guys are like talking quietly today. 9 out of 10. The probability is 9 out of 10. Does that make sense? Okay. One of the problems from last section that was graded had to do with spinners, and our next problem also has to do with spinners. We're doing an experiment, and we're going to spin the first spinner, and then we're going to spin the second spinner, and we're going to write out a sample space for the 2 spins. So a really nice way of writing out the sample space is to use Cartesian products. I don't know if you remember Cartesian products much, but they look kind of like ordered pairs. So for example, I could spin a 1 on the first spinner, followed by a 1 on the second spinner, right? Like kind of like an ordered pair. Or I could do a 1 on the first spinner and a 2 on the second spinner. Or a 1 on the first spinner and a 3 on the second spinner. What are the other things that I could do? A 2 followed by a 1. And a 2, 2, and a 2, 3. But anytime we're talking about sample space, what we're doing is we're listing out all of the options that could happen inside of curly braces. It's a set. So these are all options of what could happen when we do two spins on these two separate spinners. And then on part B, it asks us to examine the results that we just wrote down. So taking a look at those results, I'll flip back and forth between my slides. It says, what's the probability of spinning two even numbers? 1 out of 6. The only one that does that's this one, right? Yeah. So it is a 1 out of 6 probability. Number 2, spinning at least 1 2. 2 out of 6, which is, I'm sorry, 4 out of 6, which is 2 out of 3. Yeah, there we go. There are 4 of them. If you just jump to 2/3, you'd be okay. And how about spinning exactly 1 2? How many of those are there? Yeah, there's 3 of them, so we end up getting 1/2. Those 3 have exactly 1 2 spun. So we have 3 out of 6 or 1/2. Okay, so what I wanted to show you, especially with examples 2 and 3, is that when I say you have to do a tree diagram for everything, I'm not exactly saying for everything, right? There are other ways to describe all the compound different things that can happen, whatever your multi-stages end up being. But any of them end up looking like a collection of objects, right? And those are a couple of different ways that those could have looked. And that's not the only way we could have done this, right? Like I could have done a tree diagram here. I could have started out and say, oh, I can spin a 1 or I can spin a 2. And then for my 1, I can spin a 1, 2, or 3, and I can spin a 1, 2, or 3. Like I could do it that way. It wouldn't hurt anything. But it's just another option. And I wanted to show you a couple other options. All right. So I almost feel like I should change this problem. But this problem has been around for so long, I'm going to keep it. My son actually is not near as bad at staining his shirts these days. However, my little 5-year-old was wearing her Halloween costume because it's such a great idea at the beginning of October to wear your Halloween costume, and she spilled red juice all over it. So we're just going to see what happens in the washing machine because that's where I left it this morning. When I purchase a new shirt for my son, there is a 0.15 probability that he will stain it the first time he wears it, and there's absolutely no way that that was high enough when I wrote the problem. It was much higher, I'm sure. If the shirt is stained, there is a 0.2 probability that I will not be able to adequately remove the stain. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? So part of the reason I want to show you this particular example is to show you that tree diagrams don't always look like two sets of branches. And this is a really good example to show you that. So the first situation that's going on here is that when he wears the shirt, what happens? Stains or no stains? So that's our first set of branches. I mean, that is the set of branches for sure. It's either stained or it's not. So what's the likelihood or the probability that it's stained? 15, right? 0.15. So then what's the probability that it's not stained? Close? Should be 0.85. Well, remember last time, I know you haven't done any homework over this yet, but remember last time I talked about the fact that every set of branches has to add up to the number 1, 100%? That's where I'm getting the 0.85. So if I take the number 1 minus the 15, the 0.15, I get 0.85. Is everybody good with that? Okay, here's how this problem is different. When do I have to scrub the shirt? If there's a stain. So when I draw my next set of branches, I don't need 2 sets of branches. I only need 1 set of branches. The branches will be off of the word stained. Okay, so this is what happens. If the shirt's not stained, I don't have to worry about it coming out. It will be, I mean, you can draw them in there, but it doesn't help you. You're guaranteed to have the shirt look, brand new, quote unquote, for the purposes of our argument here, if it didn't get stained the first time. So there's no need to draw another set of branches off of the word no stain, because there's no scrubbing. Now, if he did stain it, there's 2 things that can happen after I scrub it. either the stain washes out or it doesn't. Does that make sense? And so along this new set of branches, we're going to use the other piece of information that we're given. How likely is it that the stain will wash out? This is where this piece right here is, so be careful how it says it. It's 0.8. The one that it won't wash out is actually the 0.2, like that. Okay, so you have to be careful, however you set up your structure, that you make sure you put the numbers in the right location. So this is the full Venn diagram, or the full tree diagram. There's nothing else that I have to do for another set of branches. Now the question. The question says, what is the probability my son's new shirt will be permanently stained after the first time that he wears it? So, where is that on this diagram? It's the 0.15 followed by the 0.2. He definitely stains it, so we're along the first branch, and then it doesn't wash out, we're along the second branch of the second set of branches. And the way that we get that, when we talked about last time, the multiplication rule, I think we called it, for tree diagrams, is you multiply the probabilities along the branch. So this would be 0.15 times 0.2. And what is that when you multiply those? Yeah, 0.03. That's like a 3% chance. That's why I know the numbers are just made up. There's no way that's high enough. No way. All right, let's take a look at another example. So a lot of the examples so far that I have done show different probabilities along different branches, right? There's different things that show up. But not all probabilities work that way, and this is a fairly good example of one. Joe says that if a family has 2 children, the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? And explain. So, a lot of you are shaking your head and saying, oh, poor Joe. No, okay, so let's take a look. He's talking about having 2 children, and so that's 2 sets of tree branches, okay? Has child number 1, and what are the options when he has child number 1? A boy or a girl? And apparently he and his wife have already talked and decided they're having a second child no matter what happens with that first one. So we're going to go ahead and draw those second tree diagram branches. And again, a boy and a girl. So we see that there's like 4 outcomes on the end. Now the fact that there's 4 outcomes doesn't necessarily mean that the answer is no to the problem. We have to put the branches probabilities in before we can actually make that claim, okay? So going back to the first set of branches, what is the likelihood that they have a boy? Yeah, so use fractions, use decimals, I don't care, but it's 1/2, agreed? How about the likelihood for having a girl? Better be the other 1/2, right? Yeah. Next set of branches, what's going to happen? Same thing. So this is an example of one where there's a 50-50 chance on each branch, so all my branches actually end up matching. Of course, that didn't happen on some of the other examples, so sometimes that happens and sometimes it doesn't. Now let's take a look at what's going on with his claim. His claim is that the probability of having 2 boys is 1/3. Well, 2 boys is right here. It's the only place where there's 2 boys listed, right? So how do I actually find the probability of having 2 boys? I multiply them. 1/2 times 1/2 is actually 1/4, not 1/3. So I'm going to not write, but I'm going to give you some verbiage, and then you can write down something in your own words that's got the same idea. What is he failing to think about when he's thinking 1/3 instead of 1/4? The probabilities start over each time you have a kid. That's a possibility, sure. What else?
There's an option to have a girl and then a boy and then a boy.
Yeah, so he's sort of like merging the boy-girl combination into one possibility, but there's actually two different ways that could happen. A boy first and a girl second, or a boy second and a girl first. And so he's merged those two things together as though they're equally likely to happen as the 1/2 of each, or the 1/2 times 1/2, the 1/4 of each of the other possibilities. So if you really think about it, and again, this is another one that you could do without a tree diagram if you wanted to, because it's all equal especially, is that you could talk about what possibilities there are, where he could have a boy-boy, a boy-girl, a girl-boy, a girl-girl. And because it's equally likely for each gender, these would all be 1/4, right? So there's one way to have a boy-boy out of 4 different ways that you could have had the two children combined. So let me pause for a second while you have a chance to write those details down. All right, so this example is a very personal example of mine. In my family, we have a genetic disease that runs in our family. It's called Huntington's disease. Has anybody ever heard of Huntington's disease? A couple people nodding. Huntington's disease is terrible. It affects your central nervous system, and it starts shutting down the ability to do certain things. So what it does is it slows down your processing time, like the time it takes your brain to tell your whatever to start or to do something. Your reaction time changes. So some of the specific memories, my grandmother had Huntington's disease, that I have of my grandmother is being at like a Golden Corral where they had the ice cream thing, and you have to stop the ice cream thing when your bowl fills up. You got them in the GC too, right? And her not having the ability to stop the ice cream machine before it was overflowing. I remember being in a car with her. I was probably about 9 or 10, and her having a small collision with the car in front of her because her reaction time that it took for her brain to tell her foot to push the brake was too long. Well, Huntington's is actually a genetic disease. So the fact that my grandmother had it meant that my father had a 50-50 shot of having it as well. And I don't claim to know a whole lot about biology, but his chances were actually even higher than that. Because what it does is it counts triplet repeats on your DNA strands and all this sort of stuff, whatever. And either my dad was going to have it, or he was going to have the chance of passing it on through a mutation as a possibility as well. So it wasn't going to be good. And so in 2001, I had been married for 3 years. My sister had been married for 1 year, and my brother was seriously dating the woman he did end up marrying a couple years later. Our family decided at Thanksgiving, now's the time to share some fun news with everybody. And so they told us that this disease, that we knew my grandma had something, but we didn't know what it was or what it meant, right? But they shared that this disease was genetic. And they also shared that not only did she have it, but my dad did too. And he had been tested for the disease, and he had it. And they were sharing that information so that the reason they were sharing it was so that we could make decisions about whether or not to have biological children. And the reason they decided at that moment to share it was because there were new advances in genealogy, research, in vitro fertilization, things like that, that even if, for instance, my brother had the disease, that he and his wife could have a child and guaranteed not have the child have the disease. So the reality is that much like our last example of boys versus girls, it's a 50-50 shot. Your kid has it, or they don't. My dad ended up having it. He didn't have the genetic mutation possibility, so that's kind of ruled out. In fact, it's very interesting because that's the part my aunt has. And it didn't have to work out that way, of course. But she does have the genetic mutation possibility where my dad has actually had the disease. At this point, my dad actually passed away from the disease about 5 years ago. So fun and exciting news on Thanksgiving, right? It's good stuff. So we were actually living in Kansas at the time, my husband and I were, and we were back visiting, and so we were staying in my parents' home, And I can like visualize like where I am, like Alicia was saying, like remembering like specific instance of learning something, right? This is kind of one of those things for me. Like I remember, I can see what the bedroom looked like, and it doesn't look like this anymore. I can see the bedroom and where we were having this discussion of what to do with this information. And what I'm about to show you with the tree diagrams is the gist of what I was doing in my brain, but without the tree diagram part of it that night as I was processing this information. So we are going to draw the tree diagram for what could happen for a family in this situation, and specifically what I was thinking that night with my family. So I am the oldest, and so these branches are actually me. And there's two possibilities. I either have the disease or I don't. And I'm just going to abbreviate it like that for now. And the likelihood along each branch is 50%. So I'll do decimals this time, 0.5s. New decimals or fractions. My sister is the second born. And so we have tree diagram branches for her next. And her branches look just like mine. She either has it or she doesn't. So I'm going to put have and don't on there, just like before. The probability along each branch is 50%, 0.5. My third and final sibling is my brother. So at the end of this tree diagram, we need one more set of branches. This is the biggest tree diagram we've done so far. I need some more space. I'm going to move it over a little bit. If you're having trouble like squeezing it all in, you probably just make your branches longer. That helps usually. So these are my brother's branches. And he either has it, have, or he doesn't. So don't. And each branch has a 0.5 probability. I would be lying if I told you that I pictured a tree diagram in my head when I did this in my head. I didn't picture this tree diagram, but I did the math that we're about to do from the tree diagram. So the question is, and was in my mind, what's the likelihood that at least one of us has this disease? That this has perpetuated for a further generation, basically. And if you take a look along these branches, the answer is pretty high. Right? In fact, every branch has somebody having the disease except for the very last one, right? And that's the math that I did in my head that night. I multiplied these three things together. So what is 0.5 times 0.5 times 0.5? It's 0.125. So how would I find the likelihood then that at least one of us does have it? There's an easy way and there's a hard way. We talked about this last time. Subtract that number from 1. That's the easy way, Emily, you're right. Yeah, so if I do 1 minus 0.125, you should have gotten 0.875, did you? So that's a scary number. It's a really scary number when it affects your family. When it affects anybody, but especially when it affects your family. And my husband and I decided right then at that moment that I would be tested, and that if I had this disease, we would not be having biological children. Flat out, period, into discussion. It was not a popular decision. My mom was really upset about that decision. in her mind, had she made that decision, none of us would have been born. And I felt like that was, an unfair way of looking at it. You're looking forward rather than backward. You can't do that with those numbers. We had discussions from her perspective of, well, how do you know that if you adopt a child that they're not going to have some problem? Well, you don't, but that wasn't the point. The point was perpetuating a disease. At least that was the way my husband and I felt about it. And so we decided. And honestly, that is probably the first time that my husband and I looked at each other and said, we need to consider whether or not we're supposed to adopt. And we decided if this happened, we were going to adopt. So that happened in 2000, what did I say? 2002? I think that was right. 2001. That happened in 2001. 2 years later, we actually were at the point where we'd been married for 5 years. And I was very young when we got married. But we were both young, so we weren't interested in having kids super fast right away anyway, because we were your guys' age, we just were. And so we waited a couple of years before we were at the point where we felt like it was time to go through all the genetic testing to know. And I was tested for the disease, and I do not have the disease. So because I do not have the disease is why I have my daughter, Abigail. If I had it, we would have never had her. But through that 2-year process of waiting to be tested, God made it abundantly clear to us that no matter how that test turned out, He wanted us to adopt. So even without knowing the outcome of that test, we had made that decision very early on, actually. Not much older than you guys are now. And one adoption led to another. And some of you know my older kids, because here on campus they are here. And then, it's very interesting when you look back and you see how God uses tragedies. Because it's tragedy that my dad had this disease. It's horrible. My dad was a very active man. The epitome of health, except for his Dr. Pepper habit. He rode bikes. It wasn't uncommon for him to get up on a Saturday morning and ride 100 miles. Who does that? I mean, really, who does that, And he was in his 50s when he passed away. So it's really tough. I have 2 siblings, my brother and my sister. Neither one of them have been tested. My sister has 3 children, and my brother has 2. And so you look at this, and you're just like, what about them? And the answer is, I have no idea. I have absolutely no idea what about them. And some of you are aware because this has happened since I've been here, but almost 3 years ago, I was unexpectedly pregnant. And, obviously I'm married, but it was still unexpected. We had not intended to have any more children. And so it was very exciting, and by the time I hit what would have been almost 12 weeks, we found out that I'd already lost the baby several weeks before. And, what do you do with that? And, my husband and I shelved it for a while, and we came back to it and talked about what did God want to show us through that. And now we have two more kids in our house. Not what we were expecting. It's interesting how God uses those things in our lives if we let Him to do something amazing as well. So one more question about this problem. So like I said, in 2003, I was tested for Huntington's disease, and I don't have it. Given that I don't have the disease, what is the probability that at least one of my siblings does? So if you take a look back over here on this tree diagram, the part of this tree diagram that this is referencing is just this part down here, right? And we can sort of ignore all of this because it didn't happen. None of that applies in the problem any longer. So we're just looking at the part inside the box. And we can do the same argument along the same red, shading that I did before. So what's the likelihood that one of my siblings has it? Well, still, the easiest way to calculate it is to calculate 1 minus the probability that neither of them do, which would be 1 minus 0.5 times 0.5. So I still look at this and I still say, there's a 75% chance that one of my siblings has this disease, and I have nieces and nephews as well. And it's scary. So, fun fact from my life, or maybe not so fun.